So we're going to be pretty hands-on. Today. So I'm going to aim to not talk for too long. So we're starting a little bit behind, but essentially what I'm planning on is for the next 10-15 minutes, talk about the motivations for dimensionality reduction. Unfortunately, I missed the previous talk. So Max, can you give me a this if I'm covering something that's already been covered? Cool. And then I'll take some questions, and I like to solicit questions not only at the end, but in the middle as well. Then I'll go into distance-based mappings, so specifically PCA, MDS, and PCR, which is principal covariance regression. And then for the main chunk of this time, I have a set of notebooks that should be in your deep note that I will have everybody go through and play around with. And those really intensely go into the math of if you had to build a PCA yourself, how you would do it, how it's related to classical MDS, etc. And then we'll take the last little bit of time to talk about complex mappings and nonlinear embeddings, as well as leave a little bit of time. I've added a couple other notebooks for those as well, although I don't anticipate we'll have too much time to get to them today. So
it's just one thing. Would you like people to raise their hand on Zoom if they have questions, or would they rather they just interrupt you?
If you can raise your hand with the little Zoom, raise your hand. I should be able to see it, no?
Yes, if you have the gallery open.
So I have a strip of the gallery, but I can make the full
Just
full-ish gallery open.
All right.
Are we good?
All right. Yes, I think we're good.
Okay, so starting, we're going to talk about the needs and the motivation for dimensionality reduction. So specifically, I, again, don't know how much work went through, but there's many different types of representations that we can use for machine-learned interatomic potential. And these vary widely in terms of the complexity and the utility of them. So for example, you might use different sort of atom density fields in one application that you might then want to use a Z matrix. Otherwise, sometimes when you're building machine learning interatomic potential, you skip representation entirely, and that's more of like the E3NN crew. But today, let's just assume that for some reason or another, you want to create features to represent your molecules or your crystals, and you need to understand those features. Specifically, I will dive into quickly the construction of one of the types of representations that we use often here in Cosmo, the smooth overlap of atomic positions. So the way that and I'm using this just as an example to kind of show what goes into one of these featurizations. So with this featurization specifically, what we do is we represent every single atom by a Gaussian field that's signed by its atomic species. And then we take the translational average of these Gaussian fields, as well as take the rotational average. And the way that this ends up being is we have we do this by representing over a density field, as well as taking over a radial basis in order to get that translational average. And the spherical harmonics will take care of our rotational invariance. And so what we get out of this is an atom-centered density that has been expanded to be rotationally and translationally. And if we're working with an averaged SOAP, permutatively invariant. So you can imagine that our resolution with these comes with the number of radial and spherical harmonic channels that we expand over. Specifically, if we were going to take a three-body vector for ethanol, for example, this is what it would look like. So this is expanded over many radial and axial channels, radial and angular channels, but essentially sitting on a singular atom, you look at all of the two-body relationships, well, three-body relationships considering the central atom, three-body relationships of that atom, and you're able to take histograms over certain radial and angular channels for each of those. Now, the reason why I'm kind of showing you this in this way is not because I expect you to understand what SOAPs are in the span of 5 minutes, but to explain the amount of information that goes into a representation for a machine learning interatomic potential. It's quite hefty, and in order to be accurate, you need to put in quite a bit of information. So for example, if we're going to take this 3-body SOAP vector, we have all of these variables that go into the dimensionality. And I'm guessing that Burke went over a bit of dimensionality of these things, but if you look at our L parameter, which determines the number of angular channels, the size of our SOAP vector is going to expand linearly with that L parameter. If we look at our N parameters, because we're taking a 3-body, we have 2 different radial channels, then it's going to expand and with N squared. And then if we look at our species, it's going to expand combinatorically. So that means that very quickly our number of features increases and our accuracy relies heavily on the number of features that we're using. But as we expand these number of features, we lose 2 things. Namely, we lose our ability to compute things cheaply, as well as we lose our interpretability. And this is where dimensionality reduction comes in. It says, in our featurization, how can we represent a lower feature space towards some end? So specifically, I'm going to talk about 2 different motivations of dimensionality reduction. So the 2 ones that I'm going to talk about are data compression. So actually taking our matrix and representing it in terms of a lower dimension matrix that contains as much data as possible, and data mapping. So specifically, we're looking at reducing the dimension of data in a way that preserves as much pertinent information as possible, or reducing the dimension of data in a way that reveals underlying relationships or phenomena. So these are 2 very different things that usually fall under the umbrella of dimensionality reduction. So either we're reducing the dimension for complexity and computational sake, or reducing the dimension for interpretability sake. And when you think about what sort of dimensionality reduction technique you're looking for, you have to think about these questions. Am I trying to just save on time, or am I actually trying to understand underlying manifolds in my data? So with that, I'm going to take a pause. I talk very fast, and as I know, so I actually finished a couple minutes earlier, but I would like to take any questions that people might have. Otherwise, I'll just have a dance party by myself here while I wait.
Well, just so I don't come next door and join you, I guess. No.
Yeah, Max is right there.
I
know I went very
Do you
fast.
have an example of one of these data mapping applications? Perhaps there's even a web application that can do this.
I will get into Chemiscope a bit, but so data mapping is typically when you have a very large data set and you're trying to understand, have I sampled correctly? Have I made sure to sample throughout all of feature space? Are we working in some sort of manifold that I'm not aware of? So think about in terms of like sampling a single species, and you're not realizing, oh, okay, I'm not actually sampling even like double bonds in my system. So it's about understanding where your data lies. Data mapping versus data compression is understanding what you can use to get rid of. Peter has a question.
Yes, I hope I can I can say what I have in my head. So
can you speak up a little bit?
Yeah, is this better?
Yeah.
Okay. So as I understood, this is about exploring the dimensionality of your data set, giving some descriptor, right?
Mm-hmm.
With some properties. So you can see, let's say for a given data set, you can see how you fill the descriptor space. And if you are over-determined, underdetermined, something like this.
Mm-hmm.
So my question is, can it help you, once you have this information, can it help you to choose the method that you will use to build the potential? Like if you want to have a neural network that has many parameters, or a linear machine learning or SOAP or something like this? Or can it be like a big?
So are you talking about determining your descriptors or determining your method for turning your materials or molecules into an interatomic potential?
So yeah, my question is, can you use this information after you chose the descriptors and explore these dimensions of the descriptor given the data set? Can it help you to choose the most appropriate model?
So I
to build
think
the potential, because the dimensionality of the descriptors will, like if you try to have a neural network to train a neural network on a feature space is not enough to fill the space of the neural network, right? It will not work. Let's say, this is my understanding, or I'm mixing these two things. But
I'm not quite sure I understand. Max, do you understand the question?
I will try to put it. So once you have this information after with your descriptor space, can it be useful for choosing the model that you use to build the interatomic potential?
So you're saying you might use this information to decide between a neural network or
between a neural network or linear model or something else. Can it be helpful, or it's just completely?
Well, I mean, you can use some of these things to understand the symmetry of your descriptor space, if that helps. Like whether you're being representative of your descriptor space, but typically, and so I come from colloidal classical mechanics, which deals with a lot of different tools. Typically, you would be choosing your different methods for building a potential based upon computational complexity a lot of the time, right?
Yes, but
so if you were able to say, okay, if I'm working in a data compression, from a data compression standpoint, I'm able to compress it into a certain number of features, that might allow you to choose a more complex method.
Okay. This answers it. So it can be used. Okay.
It can be useful, yeah.
Okay.
I mean, so some of the work that I'm not going to have time to get into today, but if people want to hit me up about, is dealing with supervised and unsupervised methods for data set subselection. And that really helps, especially if you're trying to choose like a landmark data set for a gap potential or something. So are there any other questions?
Thank you very much.
No problem. Okay, then I think I will keep chugging. So I am going to go over PCA in a much larger degree than most people have seen. So can I get a show of hands? How many people? Okay. If you feel like you understand PCA, raise your hand. If you feel like you're a PCA master, send me the party emoticon. If you feel like you're a PCA noob, then choose something else.
You have to be Zoom pro to do this, I think.
Oh, okay. I'm sorry.
Send emoticon. It's under reactions. You can do the
reactions.
Okay, thank you.
So you've heard of PCA and you feel like you get it, raise your hand. If you feel like you're a master, send me the party emoticon. Otherwise, send me whatever you feel. Okay. So I've got mostly raised hands, I think. One or two crying faces or cat emojis. I appreciate the cat emojis.
These are tears of joy.
They're tears of joy, really? Okay, great. So that means that for most of you, so some of you are either trying to still figure out where the reaction button is or don't have, or are doing their dishes right now. The rest of you. So PCA is the archetypal method because it is based on data compression. So PCA is towards that first goal, reduce the dimension of data in a way that preserves as much pertinent information as possible. So in PCA, we're essentially trying to take our data matrix and translate it into some latent space projection such that when we translate it back, we have lost as little information as possible. So it comes from this equation, where essentially we're doing an L squared loss between our original matrix and our transformed and reconstructed matrix. And I'm moving my finger around because I have animations. So essentially what we have here is a transform. So we go from this L squared loss to our understanding that our projectors are determined by the eigen decomposition of the covariance matrix. Now, I have a little exercise in here for you. Wait, I am way faster than I realized. So let's, instead of making this 38, make this 33. For anybody that wants to take a moment and try to figure out the math in between these two endpoints, I find it a very useful exercise. So how do we go from L squared loss to determining that the eigenvectors are of the covariance matrix give us the minimization of that loss? Sander, do you have a question?
No. My hand is still up, apparently. No.
Cool. And there are many routes to get from A to B here. I will show you one, but creative routes are always appreciated. The matrix cookbook online also really helps with this if you're rusty on your linear algebra. Where's my cursor?
Can I just ask a quick question?
Yeah, sure. Sorry, I was actually trying to come. I can't find my cursor right now.
That's
Sean.
okay. So to be clear, we're trying to find the P that minimizes L. Is that correct?
Correct. Yes, correct. So we're minimizing this equation with respect to P.
Okay, I just wanted to make sure.
I apologize. Yeah, I've had like 4 coffees today, so.
No, you're good. I thought that was true, but I just wasn't 100% sure.
About the coffees or the matrix?
Did my screen just go away for everybody?
It did go blank, yes.
Okay. I don't know why. I might need to just quickly start it back up. I think because I tried to annotate, it got a little mad. All right, who needs more time? We have a little bit of a buffer. Yeah, so I'll give it till 35. I can't tell if Grisali is just smiling off into the air if he's pondering on maths.
Some people have a whiteboard built into their heads.
Okay, I'm gonna call everybody back now. Who thinks that they got a solution? Okay, so I'm gonna show you how I did this. So first of all, when we're minimizing this equation, it does help us to write it out in terms of this separated product, because then when we take the trace, so when we take the Frobenius norm of a difference like this, it's equal to the trace of the outer product. And because when it's written like this, we have that identity minus that P transpose twice, that's equal to itself. And so we can reduce it and then write it here. So now what we have is we have a problem that has two separable terms. And when we take the derivative of that first term with respect to P, it equals 0. So minimizing this equation is the same as maximizing the derivative with respect to that second piece there. So we can eliminate that first piece and just maximize what we would call the similarity matrix. So L is our loss, rho is our similarity. So then we do a little bit of fun linear algebra swapping that we know that we can do cyclic rotations inside that trace and get the same answer. And then this is kind of, I feel like kind of a cheap shot on my part, but this final piece here is in the form of a Rayleigh quotient, which if you don't know a Rayleigh quotient, we can actually maximize this Rayleigh quotient when our B, our outer piece, contains the top eigenvectors of the covariance matrix. So here's how we actually go from this loss equation all the way down to the eigendecomposition. And so that's why PCA is the result of taking an eigendecomposition with respect to our covariance matrix. So what I'm going to give you now is there's a notebook. It should be in the deep note. It contains three things. It contains a walkthrough of PCA, MDS, so classical multidimensional scaling is a dimensionality reduction technique specifically for preserving data, but instead it tries to preserve the distances between data in the original Euclidean space and data in the final Euclidean space. So our latent space projection is meant to preserve the distances between data points. And then principal covariance regression, which is what a lot of us are honestly doing when we do data compression. We take our data that's compressed and then try to do some sort of prediction off of it. So when you do PCR, that means that we're actually putting into our regression the data. So I'm going to give everybody about 15-ish minutes to explore this notebook. There's a lot in here. And I will be available here on mute for questions when people have them. If you have problems getting to the notebook, it should be on Deep Note, but I also have a Git repo that I can throw into the channel for people to check out as well. Sound good? So let me just get this up.
Sorry, what was this thing that you said is helpful if your linear algebra is rusty?
Look up the Matrix Cookbook. It is incredibly useful.
Okay, thanks a lot.
It is like a reference book for matrix operations.
Okay, thank you.
So everybody, I'm just intending for you to check out Notebook 1 at this time. Notebook 2 and 3. Notebooks 2 and 3 are kind of the icing on the cake for the end. Once you are done with Notebook 1, if you get done with it in 15 minutes, just shoot me a message here and I will just put myself on mute and be here for any questions you might have.
Rose, if you're still there. Yeah.
I'm still here.
Yeah. I mean, you could also just open it on Deep Note and share the screen and walk people through it if you like. Yeah. But I think it's also good for people to try it. Yeah.
Yeah, I feel like it might be good for people. I always feel like I don't get anything when somebody's just going through a notebook on screen. But if people disagree, I'm willing to do it. But.
So the initial feedback was that I think people are interested in a bit of, not too much, but a bit of, yeah. where you can just explain a few things if they are not clear. Yeah.
Venkat, the link that you sent only has this like tiny little markdown blurb.
Okay, I see.
So there's
I
some
think that-
more. So actually, I wanted to ask. There are some more notebooks, but there's only one. There's only forward and one notebook one. So I'm wondering if maybe we're sharing the wrong notebook. Would you mind?
Yeah, sorry. Did my other ones not get loaded? So that means everybody go to the GitHub repo if you need to. But did my other ones not get loaded up, Venkat?
I can only see the first one, which is PCA, MDS, PCR.
Okay, there's 3 in total.
Oh, no, I mean,
And then there's just like a couple, like there's 3 proper ones, and then there's a couple, like, here's what notation I'm using ones. So what I'm gonna do is I'm gonna open up what I have here on my computer for people.
Yeah, the KPCA and T's UMAP come through.
Sorry, when inside joke. Because teasing is never not funny to say.
It sounds like a sneeze.
It does sound like a sneeze. Okay.
So I think I've tried to unzip the zipped thing, and I think that only had 2 notebooks.
Okay, sorry. I shared a Git repo with
Okay.
Max and Venkat before that I thought would. I have never used Deep Note before, so I apologize if I'm a little rusty.
No,
So what I'm going to do here is I'm going to share my screen for anybody that doesn't have immediate access to the notebook.
so Rose, I added it. So on Deep Note, I added the new notebooks.
Cool. So I'm just going to give everybody an overview of this, because even if we're not fully successful at getting people to use it right now, it's very useful in general.
Yeah, I totally agree.
So what this notebook does is it takes a data set of a subset of crystal structures and their NMR chemical shieldings, and it shows how we can use dimensionality reduction in order to understand this data space. So specifically, it goes through the mathematics of PCA and what the principal components represent. So hold on. With a lot of citations. So this notebook is part of a teaching series on kernel methods. So there's a lot of work that was put into this with respect to citing things and such. So for example, here, when you do the eigen decomposition, your PCA is related to the eigenvectors for the top eigenvalues. And so that means that if you want a latent space of 2 dimensions, your eigenvectors are going to be the 2 eigenvectors that correspond to the 2 largest eigenvalues. And the amount of data is related to the eigenvalue. So the percentage of data represented by the nth eigenvalue is given by the relative size of that nth eigenvalue. And so here is what this data should look like with a PCA. There are 4 clusters related to, we're using SOAP vectors here, related to the 4 chemical identities within the data set. And you can see they've separated nicely because the direction of highest variance in this data set is the chemical species. That's not true for every single data set and every single featurization, but that's true for this one. And now we can see that our reconstruction catches a lot of the different. So on the left, we have the first 2 features of our original data. And on the right, we have the first 2 features as reconstructed. And we can see that it contains a lot of the same data, although it is definitely putting more shape to this data than the original data set had. And we can use it again for out of sample data, assuming that our out of sample data lives in the same feature space as our original in sample data. So what I'm going to do is I'm going to scroll down a little bit because I didn't get to go to MDS that much. But what's really cool about MDS is in classical MDS, where we use the Euclidean distance to represent our points, it will yield the same result as PCA. And the reason being is when we construct our loss function for MDS, it's this here. It says that our loss is equal to the difference in the outer product of our original data space and the outer product of our latent space. And this is known as Torgerson scaling. Now, when we minimize this loss, it has its minimum at the same place as our loss for our PCA. And so it looks exactly the same. Now, this isn't true when you're using non-classical MDS, when you're using a different distance metric. Hold on just a sec. And you can use it as well to do with some sort of out of sample data. And then as you go through this, we also see ways to minimize the loss in linear regression. So this is actually the guts of linear regression. So if you ever want to know mathematically how linear regression works, it's on here. Showing exactly how weights are constructed for a train and test set and the importance of a regularization. And then we can use our PCA. I didn't import it yet, I'm sorry. This is what happens when you go through a notebook without entering every single cell. To actually do a linear regression, and you can see here that PCA is kind of crap when it comes to linear regressions, if those directions of highest variance don't also correspond to your directions that predict the property. And so then the notebook finally goes through the different implementations of these methods and how you might use them. So that was a very quick thing to go through a notebook that will take a lot of time if you actually want to sit down and step through the maths of everything. Also, calling out myself on now calling it maths. I've lived here too long.
You're not even in the UK. Here they call it math.
No, not everybody.
Here it's called
Those that
machine-
learn their English from UK sources call it maths.
Yeah.
I got called out before on this. Okay, so this notebook, and I'll talk about this a little bit later, came from a whole set of notebooks called the Kernel Tutorials notebooks. Which has this as well as how to do dimensionality reduction when you are knowing that you're intending to do regression later. So in that loss equation, you can actually weight it towards a loss in regression and determine a better dimensionality reduction latent space projection for that, how we use nonlinear distances as well as some other things here. So with that, I'm going to call everybody back to
Rose, so I've added you to a Slack channel called
Okay.
Day to Talk to Rose, where I think if you have additional resources like these, you can share with people because
Sounds good.
yeah. So I think in general, people are very happy to have as many links as possible so that they can try in their free time.
I have a lot of links.
Yeah, I think people would really appreciate that. Yeah, and
Cool.
for those of you who are on DeepNote, so there were two directories. There was also mlib_dr_main, which I have now removed, and there's only one, and that should have, the tutorials that Rose is referring to, all of them.
There can only be one.
Now there's only one, and there's no such thing as a file directory. That's a typo. Yeah.
So I will say the stuff that's on DeepNote are the notebooks as they specifically pertain to this workshop. The other set of notebooks contains a lot of other things that if you care, go for it. But I decided to distill down what people would be interested in today. And there's a bonus notebook in this one that's not in that. So our second motivation was data mapping. So reducing the dimension of our data in a way that reveals underlying relationships and phenomena. Now, if data compression is easy enough to understand that we're just trying to retain as much information as possible, this is kind of like the way that we project our world. There's many ways to understand the distances as they exist on the surface of the Earth, and then projecting it into 2 dimensions. There are many, many ways in order to figure out how we want to project that onto a planar surface. So with this, there's a couple different methods that I'm just going to give a kind of cursory overview to, as well as give you some notebooks to play around with. So in kernel PCA, what we do is we take our original feature space and we transform those distances non-linearly. I mean, you can do it linearly, but then you just get PCA. Because so when we're determining our PCA, they're determined by the eigenvectors of the covariance matrix. Now, the eigenvectors of the covariance matrix are distinctly related to the eigenvectors of the gram matrix, which is our linear kernel. Gram kernel is the same thing as the linear kernel. And so if we have our eigenvectors in terms of the linear kernel, we can then replace it to get our eigenvectors in terms of any kernel if we want to work in a nonlinear space. And so that means any kernel could be we're distorting things that are super nearby to be seen even closer nearby. Essentially, we're taking our distances and we're distorting them to whatever function we need them to be. And this helps, especially when we're working in some sort of non-Euclidean space, when we're working with things that are better represented by some sort of spherical representation, or we're just working with bad features that overdetermine our space. So kernel PCA uses a distance other than Euclidean distance to measure between samples and uses a lot of the same math as PCA. On the other side of things are 2 things that use very different math, t-SNE and UMAP. So with t-SNE, what we're actually trying to do is we're trying to make a latent space projection, a reduced dimension space that represents the original probability distribution. And so with this, what we essentially are doing is we're trying to say, where are things in space and how well can we represent that? And you do this by converging upon your Kullback-Leibler distance, which I will constantly call the Kullback-Leibler distance. I don't know why, which measures the difference between 2 probability distributions. And so essentially you have your original one in your original feature space and our projection. And we're taking the quotient of them and the log of that in order to determine where our minimization occurs. Now, UMAP minimizes the original and the final network connectivity. So that means for every point that we have in our feature space, we choose a number of neighbors. We make a graph over all of our points, and then we make an embedding that tries to best represent that graph in our lower dimension space. Now you can see here, these 3 things here are not meant for data compression. They're at a totally different motivation for dimensionality reduction. We're trying to understand what things lie close together, further from each other, what sort of networks we have. And so you can see why, especially if we're doing clustering or some sort of data analytics, we might choose a different method based upon what we're trying to do. So for these 2, there's notebooks 2 and 3, which show a simple implementation of kernel PCA, as well as t-SNE and UMAP with that same data set from notebook 1. So here's your screenshot slide. It's got all of the original papers on these different sorts of methods, as well as links for kernel tutorials and an upcoming book chapter on all of these things. So a lot of this I pulled for myself because I've been writing a lot about dimensionality reduction for this upcoming chapter. So with that, I think we have like 15 more minutes left in the session, which I specifically intended to leave 5 for any other questions and 10 for playing around with notebooks. So I'd be happy to take questions now. Oh, and these slides are also in the GitHub repo, so you have access to everything.
So Rose,
Mhm.
if do other people have questions or?
Is
Okay.
your question how jet lagged am I? Because the answer is very.
No, so I want to ask about picovar based or picovar. So I was not here at the beginning of the talk because I had to sort something out regarding.
So I didn't talk much about
Yeah.
picovar because in order to understand picovar, you have to understand PCA on a really deep level.
I see.
So if we go back to I went too far. I went way too far. Hold on. So if we go back to our derivation here.
Yeah.
So essentially what PCA does is it takes this loss based upon reconstruction, and that's where we derive our latent space projection. But if instead what we were to do, let me see if I can draw. I'm usually very, very bad at drawing on Zoom. If we were to weight this with some other factor here, that is our loss due to our property matrix. So projecting our X into our latent space, and then projecting our latent space back into our regression.
Right.
This would be picovar. So
Right.
picovar actually takes this additional term here and does similar math all the way down until we get that our projection is determined by the eigen decomposition of some modified covariance matrix, where that modified covariance matrix takes into account our properties as well.
Right.
I'm not going to write the modified covariance matrix because that's a mouthful. But again, knowing that the covariance and kernel matrices are deeply entwined, I can tell you that the modified kernel matrix here is just going to be a weighted sum of the linear kernels where these are approximated Ys from some sort of regression model. So that gives us something called picovar, and those dimensions are more deeply related to your target. And again, because this is built off of, where did my cursor go? It keeps doing this whenever I'm annotating. Okay. Because this is built off of this linear kernel, you could then go and replace it with any nonlinear kernel as well.
I see.
And so this is what all of those notebooks build to, is that kind of stuff, as well as Burke might be interested in this, where when you're doing CUR, which is determined by the correlation with the eigen decomposition of a set of data, you can also modify your CUR to be built upon this modified eigen decomposition and therefore get features that are directly correlated with your property of interest.
Yeah, okay, that was actually very easy to understand this way. Yeah, thanks for that.
I find the math way more informative than the hand waving
Yeah.
is.
This is actually because I don't think I understood the loss function before this, but it's really clear that the loss is basically trying to see how much you can recover Y on the basis of a low dimensional projection.
My goal here was to let the people get their hands really into the PCA so that next time everybody does the little party response. And then that way, when you're thinking critically about the different other dimensionality reduction techniques, which you can really think about, is this PCA in another hat? Is how are we working in our latent space here?
Yeah, that makes sense.
Because LLE, ISOMAP, SketchMap, and MDS, they're all PCA in another hat. They're all just distorting your distances and then taking some sort of eigen decomposition. All right, so we still have 10 minutes for exploration and questions. again, I didn't want to overload people with a bunch of slides. I just wanted to let them play.
Yeah, I mean, I think I have more questions, but I think it's better if other people ask. So I'll mute myself for some time.
Sean, you have a question?
Yes, just actually about what you wrote. I don't fully understand it, but I just want to make sure I'm confirming. So this factor that's now weighted with 1 minus alpha, that's y minus x times the p's.
So essentially what this is saying is if we're building a latent space projection with the intention of doing regression on it. So I'm sorry, I don't see my cursor. So this here is equal to our latent space projection. The xpxt is our latent space projection. So that's essentially saying we know we're going to do PCR. So if we know we're going to do PCR, how can we build our projection such to minimize the loss in our eventual regression?
I see. Okay. Thank you.
No problem.
I also have a question, in fact, because earlier in the talk, you mentioned that you might use this for feature compression, right? So what would the difference be between using this for feature and sample compression? And can you maybe comment on the difference between those two in sort of a kernel type of method? Because I think many people here will be more familiar with neural networks than kernel methods.
What do you mean in terms of sample compression?
So maybe you can just explain a little bit more what the X matrix represents.
Oh,
and
the
then
X
what you mean
matrix
by
here
covariance
represents, okay, so each row is a different sample. And so typically, if you're thinking about the X matrix being features in every single column, so if you're working in a neural network, depending on what kind of neural network you're running, you have to feed in some sort of information for every single sample. So correct me if I'm wrong, Max, but with GAP, you actually need to feed in features, yes?
Yes, and build a kernel matrix out of those features.
Yeah, and so with GAP, you're working with some sort of symmetrized features. Again, come from a different area. And you'll typically select some sort of landmark set on which to reference your features. Sorry, reference your samples. You can use similar ideas to determine which landmark set you should use, as well as which sort of features you should retain in order to make that kernel. So I can throw in, I didn't want to kind of do like a self-demonstration of just showing everybody my work and my papers. But I can throw in my 2 papers, one of which is extending this dimensionality reduction technique for kernelized methods, and the other is modifying traditional sampling methods using this, this biased distance space, feature space.
When you say traditional sampling methods, you mean for like sampling just some sort of bucket of atomic configurations to get
atomic configurations, features, anything that you know that you eventually want a regression from. Because when you know that you want a regression, that changes the importance of certain things. And all of this is implemented in an open source library. I'll dump a bunch of links for people.
Yes, please do advertise Psi-k Cosmo. This is the perfect place to do that.
I always feel weird like giving these tutorials and being like, how much do I mention my own work?
That's why we invited you. But yeah, are there any other questions? We have 5 more minutes.
Yeah, I intended this for
started 5
people to
minutes
play
late.
around with notebooks. I don't know if people are actually doing that.
How about, oh right, Linux people can't do reactions. I say Linux people. People using Zoom on Linux can't do reactions. But if you can do a reaction, maybe you react with
So I can see people on DeepNote running these. So I think, or at least browsing through the.
Yeah.
Yeah.
Great.
Yes, I can personally attest that Kernel Tutorials provides many. It's enough material for a semester course, almost, let's say. So it's enough material to keep a student busy for weeks.
It's enough material to keep me busy writing it for for months.
Always takes longer to write than it does to present it, doesn't it?
Yeah, because I needle myself about words all the time. So I just dropped my 2 papers in MLST in the Slack channel. So yeah, they're both incredibly pedagogic with a lot of math. So buyer beware. But I'm always available to talk about things. And
Yeah. So Rose, I think the way this is going on, most people will maybe take this evening or tomorrow morning to go through these and ask questions in the Slack channel. So
cool.
yeah, so that's
I
how it
am
has been so far. Yeah.
generally available during the day, and I usually turn my Slack off at night because Slack notifications can cause panic when I'm waking up in the middle of the night.
Yes, I hear you.
You also slow down my computer considerably. You wake up and get 25 of them from a certain person.
Yeah.
I have no
Like,
idea
this
what
is
you're
recording.
talking about.
Oops.
Yeah, especially when you have a conversation between 2 people on random and it ends up giving you 50 notifications when you wake up. Yeah.
Right.
All right.
People, do
I'll
we
be
have
around for
time? 28,
questions.
okay. All right. And in the meantime, whoever has this
So-
turned on and is listening,
So can I ask a
actually,
question?
so this is especially directed also to the speakers because we're having a poster session, but we need to know how many people to expect at the poster session. So if you can just fill out on the both on the website, and I'm about to send it to the Slack. There's a very short form. It should only take you 2 minutes at most, just so you can get numbers for the poster session and the social dinner. So please fill that out if you get the chance, speakers and participants alike.
So Rose, can I ask one question? If you're still available.
Never, unacceptable. No questions. Go for it.
All right. I was just wondering, so I know that for kernels, I mean, there is a computational cost that scales with the number of features, so specification is important. But do you think for, so do you think, again, this is just my ignorance, but is this as important also in the case of, let's say, neural networks or deep
Yeah,
networks which are being used for big data?
So the second paper that I sent, Edgar, who's somewhere around here, was one of my co-authors because what we did is we did feature selection on SOAP features in order to put them into a Boa Parnell neural network. And what we essentially showed is 2 things were cool. Well, if you add in supervision on a linear, with a linear model, Edgar turns on his video, with a linear model for the CUR feature selection that greatly improves your performance in your neural network, as well as improves the performance of your linear model so well it does better than a poorly chosen set of features for a neural network. So feature selection is incredibly important, and even choosing them using linear relationships, the benefits trickle down in towards nonlinear models.
Yeah, and I mean, just to add to that, I suppose if you think about execution times for, say, neural network potential, then ultimately one of the key steps is actually calculating the features, and depending what exact strategy you use for this and how you select them, right, you can cut down substantially on the time spent computing features and therefore on the time spent evaluating and say energies and forces from a neural network potential. So you stand to gain.
And then also because that's the difference with doing like a feature preserving versus feature constructing dimensionality reduction. So if you're actually doing feature selection, you don't have to recompute things, which is very important compared to doing a PCA and then building something off of that PCA. You have to recompute everything when you do a PCA.
And you have to start by computing everything that goes into your redefined set of features, whilst if you select, you stand to gain from only calculating a subset of what you originally proposed as features. And so this is, I mean, for example, the default case, Bela-Parinello neural network potentials, you can you define in your input which particular features you actually want to evaluate. And if
Edgar,
can
are you
cut down that
touching
number-
on, are you touching on feature selection in your talk?
No, practically not.
Okay. So I'll let everybody know there's a whole CUR notebook in the Kernel Tutorials notebooks if you want to play around with it. I also, I'll drop it. Whenever I give a talk, not today because it's fairly low on slides, I put my slides on my website. And so if you want to walk through one of the talks that I gave on that more recent work, there's a couple ones in there. So I will drop that as well. Just my website because it's just my name. All right, I'm gonna mute and turn off video.
All right,
and-
thank you so
and go
much,
get a
Rose.
snack.
Thank you, Rosie, for the talk and tutorial. And yeah, so as I said, if you haven't already signed up for the poster sessions and things, please do that now.